All right. So let's say that we're asked to solve the triangle who has angle A of 36 degrees, side A of 2, and side B of 7. If we draw a little picture of what this thing might look like, this picture is not to scale. So A here is 36. The side A opposite it is 2. I'm going to call this angle B. So this one is B. This would be angle C. So that's side C. Notice that it didn't matter really where I labeled angle B and angle C since the drawing was not to scale. Everybody's okay here? From the drawing, hopefully you notice that this is the side angle situation. And if we review our criteria for the side angle situation, we are in the acute. The angle that's given to us is acute. And the side opposite that angle is less than the other side that's given. Is everybody on board with how we can see that? Since 2 is clearly less than 7. So, this means we're in the 2 solution situation. That's okay. So we'll start by using the law of sines. So we can say sine of angle A over side A is equal to sine of angle B over side B. Hi, Selena. Thank you. Now we'll solve this for angle B. So I have 2 sine B is equal to 7 sine 36. And I'll divide both sides by 2. And then we'll take the sine inverse of both sides. What mode should my calculator be in to do this? It should be in degree mode. And when I do that, I get yeah, we got an error. Why did we get an error? What does 7 sine 36 over 2 give us? It's bigger than 1. Can we take the sine inverse of that? No. So what does that imply? There's no triangle possible there. Sure, that's not incorrect. So let's do one that's not quite so silly. So again, I'll just kind of start by drawing a triangle. Again, this is not to scale. So just like before, notice again the situation that I'm in, side, angle, and I have A is acute, and side A is less than side B. So 2 triangles maybe? So let's try this. So sine 30 over 6 equals sine B over 7. And we'll cross multiply and divide again. Not very legible. So that gets me to here. And then when we do the sine inverse of both sides, we get this. And when I plug that into my calculator, I get well, when I look at 7 times sine 30 over 6, that's less than 1. And that we can take the sine inverse of. Does that make sense there, Julia? Okay. So the issue is when you have something like this, if that was only 2, there's no way to kind of, well, let's say it would actually be like here would be too long. There's no way to extend that side long enough to intersect without making, when it's still keeping it at that angle kind of thing. So they just wouldn't connect, if you think about it from a picture standpoint. Does that kind of make sense? Okay. Bella. Yes, so I just typed that into my calculator. Yep. That's exactly how I got that. So that's for triangle 1. That's the value for B. Let's find the other values in triangle 1, and then we'll move on and find the stuff for triangle 2. Okay? So how can I find angle C in triangle 1? Yeah, I know there's 180 degrees total. I know angle A was 30. I know angle B is 35.7. So angle C has to be 180 minus 30 minus that. So 114.3 is what I got. Everybody okay there? Now that I have that, I can find little c by just using the law of sines again. So I can do sine A over A equals sine C over C. And then we'll cross multiply and divide. So I just need to type that into my calculator. And I get about 10.9. Is everybody happy so far? Now let's find triangle 2. So to do that, I know that this angle was 35.7. Sine is also positive in the second quadrant here at 35.7. Everybody agree with that? So I'm looking for that angle. That's 180 minus 35.7. Is it always going to be 180 minus whatever your answer for the first triangle was? Yup. If you do (180 minus angle A) and it's a two-triangle situation, or 180 minus your answer in a two-triangle situation, that should always give you what you're looking for. It should always be, one should always be acute and the other should always be obtuse. If the first answer you got was obtuse, can you get an acute one out of it? No. No. It should always go acute then obtuse. Everybody good with that? Now we're going to do the exact same steps as we did before, but instead of using my angle B of 35.7, I'm going to use this angle B of 144.3. So how can I find angle C? 180 minus 30 minus 144.3. Exactly the same way that we did here, just we're using our other angle B. And then how can we solve for C? Well, I'm going to do the exact same thing as I did over here, but instead of using this angle C, I'm going to use this angle C, the angle C in my second triangle. So cross multiply and divide. And when I type that in, I get about 1.2. So finding that second triangle really isn't terribly tricky, right? It's the exact same process you used the first time. It's recognizing when you need to go looking for it that's the tricky part, right? And when do we need to go looking? We need to have an acute angle. Oh, we need to have the SSA situation. We need to have an acute angle. And then the side opposite the angle has to be shorter than the other side that's given to us. Okay, so let's do some story problem examples using the law of sines or law of cosines. So the following is from page 437. This is example 4 from your textbook. It says the forest ranger Chris Johnson at Ranger Station A sights a fire in the direction 32 degrees east of north. Ranger Rick Thorpe at Ranger Station B, 10 miles due east of A, sights the same fire on a line 48 degrees west of north. Find the distance from each ranger station to the fire. So you've also been included, kindly enough, a picture in this, but let's pretend that we didn't get the picture. So it says that Ranger Chris Johnson at Station A sights a fire in the direction 30 degrees east of north. So I'm going to call this Ranger Station A. If I'm going to draw north, north is straight up, right? So I'm going to imagine I have like a little imaginary compass rose here. Everybody okay with that idea? So when it says east of north, means we're starting on the north line, and we're going to go east 32 degrees. Everybody okay with that idea? And I'll call this point F the fire. Maybe I should have drawn it in red. Those are supposed to be flames. It says Ranger Thorpe is located at Station B, 10 miles due east of E. Or I'm sorry, due east of A. So we have that. Notice that in our compass rose, east is that direction. Everybody agree with that? And it says that this guy sights the fire at 48 degrees west of north. So start at the north line and go 48 degrees. Maybe that's... Everybody okay with how I drawn my picture? Okay. What's the issue with this picture, though? I don't know any of the interior angles of this triangle. But that's not so bad. I can find the interior angle A here pretty easily. How can I find that? From what? From 90. Right? Why 90? Because that is a right angle, correct? Everybody agree with that? So, A is equal to 90 minus 32. Or 58. Who can tell me then what angle B is going to be then? Good. How do we get it? 90 minus 48, so 42 degrees. And now that we have those, what can we get really easily? The third angle, angle F. How can I get that? Yeah, 180 minus 42 minus 58. Or add them together and then subtract. Either way of doing it is fine. So I get 80 degrees there. Okay? The problem asks us to find how far each of them are away from the fire. So we're looking for the little a and the little b in this case, side A and side B. Everybody okay with that idea? So let's say we want to solve A first. Which equation would I want to use here? Law of sines or law of cosines? Law of sines. Hopefully it's obvious to us that we have an angle side angle situation. And what equation would I write then? Very good. And now all we need to do is cross multiply and divide and get that A is 10 times sine 58 over sine 80. And we'll type that into our calculator. Somebody's watching something funny. So we have 8.1 miles when we type that in. How are we going to solve for B? Virtually the same thing. Good. What equation would I write? Good. Sine 80 over 10 equals sine 42 over B. And then we cross multiply and divide and get B is equal to 10 times sine 42 divided by sine 80. And we do that, we get about 6.8. So, how much different was this than the just solving problem? Than solving a triangle? It's virtually identical, right? What's the only hard part? Probably drawing the picture, right? That's probably the hardest part. But that should be your first step in any of these story problems. It's you're solving a triangle. Turn the picture into a stinking triangle. If you can't draw a triangle out of the picture or out of the story, read it again, because there's a triangle in there somewhere that you should be drawing, right? If your picture doesn't look like a triangle, read it again and go, I'm not understanding something about this. All right, let's do one more story problem example. This one comes from page 445, example 5. It says the bases on a baseball diamond are 90 feet apart, and the front edge of the pitcher's rubber is 60.5 feet from the back corner of home plate. Find the distance from the center of the front edge of the pitcher's rubber to the far corner of the first base. Okay, so let's draw ourselves a picture. So, a baseball diamond, hopefully we all kind of know what that looks like, right? So this is home, first, second, and third, right? And it tells us that each of these baselines, or each base is 90 feet apart. So those are all 90. And the pitcher's rubber is here. And we're told that from the home plate to the pitcher's rubber is 60.5 feet. And we're asked then how far is it from, what did it ask for again? Find the distance from the center of the front edge of the pitcher's rubber to the far corner of first base. So we want that length there. No. The reason it's not, it looks like a right triangle by the way we've drawn it. But if you've ever been on a baseball field, you know, for the pitching rubber isn't exactly in line with first base. I just kind of drawn it poorly. There are right angles here, though, and that is going to be important to us. What do happen at right angles? These spots happen at right angles, correct? Everybody agree with that? Have you been on a baseball diamond? Well, okay, fair enough, but that's how we know that, is it's from the construction of a baseball diamond. There was a picture given in the book. It does show the right angles. Because you know what the right angle symbols are? The base, which is the square in the corner, is how it's drawn in the picture. But everybody so far so good? Now, we do know something, though, about the relationship between the pitcher's rubber and home plate. Those are located directly in line from each other, correct? And we know that this pitcher's rubber is, hopefully, if you've ever been on a baseball diamond, halfway in between first and third base also, correct? Everybody's okay with that idea? So what that tells me then is that this angle is 45 degrees. And if you really wanted to, I can tell you the theorem from geometry that we use to do that. But it's basically that if I consider this triangle here, that's an isosceles triangle, correct? This thing is the height of an isosceles triangle, and the height of every isosceles triangle is going to bisect that central angle, or that apex angle there. So that's the geometry theorem that we use to say that. That was maybe a little bit more overkill than maybe you really cared. So if we look, which situation are we in? S, A, S. That means law of cosines. So I can say that x squared is equal to 60.5 squared plus 90 squared minus 2 times 60.5 times 90 times cosine of 45. So, calculator time, 60.5 squared plus 90 squared minus 2 times 60.5 times 90 times cosine 45. That gets me approximately 4,059.9. Is that my answer? It definitely can't be that far. Well, that's a far throw. Good luck with that, baseball stars. What do we need to do to that? Yeah, take the square root of that. And when I do that, I get 63.7